Okay, so we'll look at permutations here. So a permutation is an arrangement. Okay, that's the best way I can kind of describe it here, as an arrangement. So it's an arrangement of a number of objects in a certain order. Okay, the idea here is that order, and even if we want to stick with P, position, matters. The idea there is ABC is not the same as CBA, which is not the same as BAC. Even though all three letters are the same, the order that they're in has a meaning here. And those would be considered three different arrangements of those letters. If I was just asked to group three letters or to pick a group of three letters, those would be the same group. But here, if I'm asked for a particular arrangement, position matters here, and those would be considered different. One of the ways we can tie that back to something that we have looked at is the factorial. N factorial represents the number of arrangement of n objects. And think even of your fundamental principle of counting. If I have, let's say, 4 objects, there are 4 that could go in the first one, 3 in the second, 2 in the first, 1 in the last, and that is just 4 factorial. So very closely related to like our fundamental principle of counting, and of course to our factorial then on the whole there as well. When we're looking at permutations, the rule that we could use, or that we can use, is n factorial over n minus or factorial. Okay, and that will always give us the number of permutations that I have of a certain number of objects here. So if I want to arrange or objects out of n objects, this will give me the total number of arrangements that I could have here. If we think about it in practice, if I have 7 objects and we want to arrange 5, that's 7 by 6 by 5 by 4 by 3 by 2 by 1 over 2 by 1 here, which is 7 by 6 by 5 by 4 by 3. And those essentially are the 5 spaces that I'm looking to arrange here. Okay, so I have 7 options for the first, 6 for the next, 5, 4, and 3, 2 left over, which makes sense there. Okay, so really this is just a way of, I suppose, denoting or making kind of theoretical what we're doing in these questions. I have put a note here as well of that you should know this formula, but at the same time it's often much easier to use boxes to help us visualize these questions with the boxes, like I've nearly been doing here in kind of explaining these examples. So when we're looking at permutations, the steps I would tell you to follow would be to understand the problem. So look at the objects we need to arrange and look at if there's any restrictions. The restrictions could be that maybe certain objects need to be together or certain objects need to be in a certain place. We might be asked to start with one object. We might be asked to have one object in the middle. And all of these things would obviously have a big impact on the overall arrangements there. We look at the restrictions then. If we're asked to put something in a particular place, that means there's only one option for that place or 2 options for that place, and that's going to reduce the options then in later spots in the arrangement there. If we're asked to group some objects together, what we will do is we will treat those objects as nearly one unit that's going to be moved across the arrangement there as one thing, which then in turn is going to reduce the total number of objects to be arranged. What we have to remember in that case is we need to multiply the number of arrangements by the possible arrangements of that block. So let's say I'm arranging 7 people for a photograph and 3 girls want to be together, then that's fine. I can look at all of the ways that I could put these 3 girls, so start with them or have them in second place or third place or whatever, but I also need to consider that those 3 girls could swap places within their kind of seats there as well. If there's no restrictions, the total number of arrangements for any kind of arrangement we have would just be n factorial, and if there are restrictions, we'll work with our boxes then to reduce that down. Okay, so let's have a look. How many ways are there of arranging the word Tuesday? So Tuesday, 7 letters. The total number of ways of arranging 7 things is 7 factorial, and 7 factorial, I always lose this button. There we go, nice. 5040. So 5040 ways of arranging the letters in the word Tuesday. How many arrangements begin with S and end with a vowel? So let's set this one out using our boxes here. So I'm basically saying there are 7 places or orders, places I suppose is the best one, positions in this arrangement here, accounting for the 7 letters, we've been told we have to start with S, which means there is only one option for this first box. We are then allowed to finish with a vowel, so that could be U, E, or A. So there's 3 options for that last box. We bear in mind, though, that we will only use 1 in the first box and 1 in the last box. Even though there are 3 options, only one of them is ever going to be used. So for this second box, there are now 5 options. There's 4 for the next one, 3 for the next one, 2 for the next one, and then 1 for the last one. Okay, we can multiply that out as normal. We could rewrite it as 1 times 5 factorial times 3 if we wanted to, doesn't really matter. But let's go with that. So 3 times 5 factorial is 360. So there's 360 different arrangements of that scenario there. If we're asked how many arrangements have the letters D and Y together, we're saying that there is now 6 objects to be arranged. Those are the letters T, U, E, S, A, and then the block of D, Y. Okay, so only 6 objects to arrange. Okay, so the number of ways of arranging 6 objects is 6 factorial. That's the 6 objects. We also then need to multiply that by 2 factorial, which is the arrangements of D, Y. So what we're saying here is that there are 6 factorial ways of arranging those letters, so T, U, E, S, A, and then this D, Y combination. There's 6 factorial ways of arranging that. Of those options then, there's also the choice of having Y first, so doing a T, U, E, S, A, and then doing Y, D. So that's 2 factorial different ways of arranging those that block there of D, Y. So multiplying those, 6 factorial times 2 factorial gives me 1,440 possible arrangements here, following that restriction. Okay, we'll get into some of these questions because some of these can get a little bit tricky. So it's just about kind of taking them slowly and kind of really thinking your way through them. So Seamus needs to pick a new PIN code. It must be a 4-digit code. It must use exactly 4 of the digits from 1 to 9, so no digit can be used more than once. Work out how many such codes are possible. So Sean's PIN code has 4 digits, so we'll lay them out here. These are our 4 digits. We've 9 options for the first one, then 8, then 7, then 6. That's that idea of that factorial when we had 9 factorial and then 9 minus 4 factorial. Okay, but also we can just do it by doing 9 by 8 by 7 by 6, which gives me 3,024 different codes that he could have. We want to work out how many codes contain the digit 2. Okay, so we need to think about all of the different arrangements that could come from that digit 2 there as well. Okay, so let's have a look at that. Well, we have only 3 to look at now. Okay, we've only 3 different ones to look at. So we've 8 options for this one, 7 options for this one, and 6 options for this one, which is 336. Okay, so we've 336 different arrangements there of these three letters here. Okay, and then we have 4 different arrangements. Okay, for my number 2. There's 4 different places my number 2 could be in within that arrangement there. So that gives me a total of 1,344 possible codes. So I'm basically saying there we could start with 2, we could go 1 and then 2, we could go 1, 1, 2, and we could do 2 there in the 3rd position there as well. So there's 4 different ways that I could arrange my codes there for 2, and then there were 336 different ways of arranging the 3 remaining letters there. Okay, so let's keep going. Work out how many of the codes in part B have the sum of their first 3 digits equal to the 4th digits. Okay, the codes can contain the digit 2, but they don't have to. Okay, so let's have a look at them. So the sum of their first three digits equal to the fourth digit. So we could have 1, 2, 3, and that would give me 6. Okay, so 1 plus 2 plus 3 equals 6. We could do 2, 3, 4, and 7. Or, no, and 9, excuse me, not 7. Okay, let me see, I'm going to copy some of these down. We could do 1, 2, 4, and 7. 1, 3, 4, and 8. We could do 1, 2, 5, and 8. We could do 1, 2, 6, and 9. I'm just kind of working through them here in order. 1, 3, 5, and 9. Okay, we could work out all of these. So we're basically saying here there are 7 different arrangements here where the codes would add up to, where the first 3 digits of the code would add up to the last digit. Okay, now looking at that as well though, we can arrange the first 3 in any order. They just have to add up to give the last. So the number of ways of arranging those first 3 digits is 3 factorial. So we have 3 factorial ways of arranging all 7 different codes, which is 42. So there are 42 different codes that satisfy this requested scenario here. Okay, a little bit of work there even just in listing out the different codes that we can get, but you kind of treat it as the lowest digit is 1. Okay, so, and I suppose what that means is maybe the biggest digit, I suppose obviously the biggest digit we can make is 9, but by including 1 we're kind of limiting ourselves maybe to a maximum of 8 amongst the other digits. So just kind of bearing all of that in mind really. So we'll continue onwards anyway, look at some more security codes. So a security code consists of 6 digits chosen at random from the digits 0 to 9, so that's 10 digits. The code may begin with 0 and digits may be repeated. Find how many of the codes will end with a 0. So let's consider that. 6 digits need to be chosen. We are basically saying there's only one choice for the last digit because it has to be 0. There are 10 choices for the first ones. So 10 by 10 by 10 by 10 by 10, so 10 to the power of 5, which is 100,000 codes. So 100,000 codes will end with a 0. Okay, find how many possible codes will contain the digits 2018 together and in this order. So that's slightly important for us here. So we want to include the digits 2018, which only leaves me 2 other possible digits to include here as well. So what that means is we're arranging 3 objects. That block of 2018 and then the additional 2 other codes there that need to be included. Okay, so those are kind of the only different arrangements that we're trying to do here. So we want to arrange those 3 different objects. Okay, we have 10 choices for this one and we have 10 choices for this one. Okay, so we have 10 choices for the first one and we have 10 choices for the last one there. Okay, and then we've that one choice. So let me see, I'm setting this up with my boxes. 10 choices for the first one, 10 choices for the second one, and then 1 choice for the last one, which is my block of 2018. And also then there are 3 different ways that I could arrange that. I could have the 2018 in the first, second, or third position. Okay, I could have the 2018 in any of those. So that's 100 times 3, which is 300. Okay, so 300 different codes or arrangements possible for that one there. Okay, let's keep going. 2 adults and 4 children stand in a row for a photograph. How many different arrangements are possible if the 4 children are between the 2 adults? Okay, so we have to have 1 adult here at the start. Then we want to have the 4 children, the block of 4 children, and then we want to have 1 adult again at the end here. Okay, so we have 2 options for the first adult, 1 option for the last. So there's 2 arrangements of this scenario here. So there's 2 different ways. I can start with 1 adult or start with the other adult. We also then need to consider that there are 4 factorial different ways of arranging the children within the scenario here. So there's 4 factorial different ways of arranging those children. So 2 times 4 factorial, which gives me an answer of 48. Okay, what can kind of happen with these questions here is we kind of want to use the factorial, and I even find myself that in some of those previous questions they're like wanting to use the factorial, like this idea of arranging the three objects, wanting to do factorial with that as well, the kind of 3 by 2 by 1. But it's kind of important to consider that that's more to do with the kind of overall number of objects that I'm trying to arrange here. So really out of this I was trying to maybe arrange out of not necessarily 3 objects, because there were still 10 choices for the other 2 points here. And the same thing comes in here. It's not necessarily 3 objects that I'm arranging. There's 3 different positions to consider here, but I'm arranging more than 3 objects because I have my 2 adults and then kind of the 4 children themselves. But there's only really 2 arrangements there. I start with 1 adult or I start with the other adult. The children are kind of a fixed variable there in that one, but there are then 4 arrangements of the children within that. Okay, we'll look at the deferred paper. I always get a bit nervous when it's deferred paper questions because some of these can be kind of tricky. So, in how many ways can the letters education be arranged if each letter is used exactly once in each arrangement? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 factorial different ways of arranging that, which is 3, 6, 2, 8, 8, 0. In how many arrangements do all of the vowels come together? So we take them as one block. So that's A, E, I, O, U, literally all the vowels. Okay, so we take these as one block. So there's 5 factorial different arrangements of that. Okay, there's 5 factorial different arrangements of that block to be considered. We're arranging 5 objects because there's no restriction on the order here. Okay, in some of the previous ones we've had a bit of restriction on the order in terms of what needs to be first or not. Here, no restriction. We're arranging these 5 objects, the letters, and then each of these different and then each of the different the vowel block here, and then all of the other letters. And I suppose the additional point here is that no letters are left out, and that can be where our factorial kind of fails a little bit, is if any letters need to be left out here. We're arranging 5 objects. Okay, so that is the letters E, D, C, T, N, and then my block as well. Okay, so, or sorry, not E, of course, D, C, T, N, and my block. Okay, need to be arranged, so that's 5 factorial. There's also 5 factorial ways of arranging those vowels within that block. So we can multiply this to get 14400. In how many of these arrangements will the letters A, C, T, I, O, N be together and in that order? So that's important as well to consider. So we now have, let me see, 1, 2, 3, 4, 5, 6. So we have a block of 6, and then that leaves me with 3 other letters. So we have 4 factorial arrangements of these 4 objects because we have 3 letters and the block then. So 4 factorial arrangements of these objects, which is 24, and we are only arranging that block in one way, just in that order that's given. So there's only 24 arrangements of that. Okay, so you can see what I mean there working through some of these questions, where the use of boxes to kind of highlight just the positions that we're looking for can be quite helpful. I suppose we saw here with some of these ones, and even this one here as well, and some of these other ones, that looking at the position that maybe a particular value could be in can be quite important here in determining whether there are other arrangements or outcomes that need to be considered here as well. So like the 2 in this example, or looking at the arrangement of the block here with the codes where the 2018s together and then the other codes remain the same, and looking at the kind of 3 different ways that could be arranged. But on the whole, it's maybe being familiar with that idea, the steps that we've identified here to help us kind of arrange or handle restrictions as well if there's fixed positions or objects coming together, and then looking at even that formula to a lesser extent but still being familiar with it, but even focusing on those boxes to help us with position and order to help us with the questions.